Hi, I'm Usher, and today I'm going to present our work Adaptive Spatially Aware I/O for Multi-Resolution Particle Data Layouts. This work that I'm presenting today focuses on addressing challenges when working with large data sets in the simulation visualization pipeline. So at a high level, we have a parallel simulation. This is then outputting a large amount of data using some I/O library, shown in orange, potentially with its own I/O optimized data layout. This data can then be visualized post hoc or in situ, and this is one of the paths that leads to scientific insight. The data is typically produced by a parallel simulation running on an HPC system on thousands to hundreds of thousands of cores. To output the data, the data output size can be from hundreds of gigabytes to terabytes per time step. And this data is output as a raw dump, typically using a parallel I/O library. However, post-hoc viz tasks typically rely on a viz-focused data layout to provide multi-resolution reads and spatial or attribute filtering. These post-hoc visualization tasks can be run in parallel on an HPC system for full resolution rendering of these massive datasets, or locally on a laptop or workstation by taking advantage of some filtering or multi-resolution streaming to allow long-running exploratory sessions, which may be inconvenient on an HPC system, or to use latency-sensitive VR systems for immersive visualization. The simulation data can also become so large that it cannot be saved out at a high enough temporal or spatial resolution to perform the desired visualization tasks, requiring the use of in-situ visualization. In-situ runs the visualization during the simulation, for example, in the same process, or in a different one that fetches data over the network. And our focus in this work is on the data layout bottleneck that exists between the simulation, outputting the data, and the visualization tasks. And so what I mean here is that prior parallel I/O strategies for particle data do not output a visualization-tailored data layout. So to achieve high bandwidth I/O, simulation I/O libraries optimize for high bandwidth full data writes and reads at large scales, large levels of parallelism, and to minimize the amount of time and computation that takes place during I/O, they typically perform a raw data output. So there's no higher level acceleration structures that are output by these libraries. However, to support visualization tasks on less powerful or more demanding systems like VR, visualization tasks typically rely on low latency multi-resolution reads of subsets of the data. And these are provided through some form of hierarchical or indexed data layout that allows fast access to subsets of the data or multi-resolution representations of the data. And as a result, there is an expensive data layout conversion and duplication step that typically takes place if the scientist wants to make use of one of these visualization tools that can require the conversion and duplication of potentially terabytes of data. And so when I say that the prior particle I/O strategies do not output a data layout well suited to visualization, there are scalable I/O libraries for particle data. However, the output structure is not defined to be, say, spatially coherent. So for example, here for hack generic I/O, it has been demonstrated to achieve very highly scalable I/O. However, the assignment of data into files, subfiles, is not necessarily spatially coherent. So for example, if we have 16 ranks grouped into 4 files, shown here by the color coding, we could have a worst case scenario like this, which may not be the worst case in terms of network topology, but it is the worst case in terms of visualization tasks, where we may want to read this box of the data later, and this means that our viz task has to open 4 different files and perform seeks and reads within these files to access the data. Hack also includes a PNetCDF writer to work with other tools that support PNetCDF. And this outputs some metadata about each rank's block of data within this particles array, as shown here, with the index. However, these blocks are not merged into coarser grids, nor is a more complex data layout built, and so there will still be scattered reads required to load multiple blocks. And furthermore, in contrast to the generic I/O writer, the PNetCDF writer uses a single shared file parallel I/O strategy, and this is known to not scale, as well as a subfiling or two-phase I/O strategy. HDF5 also supports a subfiling output strategy. However, HDF5 treats the particles as 1D arrays of memory, and is thus unable to perform a spatially aware grouping or construct or output a visualization-focused data layout. Our own prior work, Kumar et al. 2019, on the adjustable uniform grid for spatially aware particle I/O does output a viz-tailored file structure with a level of detail of particle ordering just by reshuffling the particles. However, this previous approach relies on three assumptions about the particle distribution to allow it to optimize for speed of the I/O pipeline. The first is that some ranks may not have particles, as shown here. The second is that the ranks that do have particles have approximately the same number of them, also as shown here, where each rank has about 6 particles. And finally, the assumption that a box can be placed in the domain that contains only the ranks with particles. This holds for some simulations like classical molecular dynamics or material point method, or early time steps of cosmology simulations. However, it doesn't hold for a large class of simulations that have non-uniform particle distributions like those shown on the right. These distributions violate assumptions 2 and 3. So the ranks with particles do not have approximately the same number. They're highly non-uniform in their distribution, and it's not possible to place a box that contains only these ranks. These distributions can happen in a large number of simulation domains listed here. So material point method, cosmology, as gravity acts on the particles and clumps them closer together, and free surface and dispersed multi-phase fluid dynamics, or direct simulation, Monte Carlo, and combustion simulations. A new approach is needed to provide scalable I/O while outputting a viz-tailored data layout for these simulations. So our work introduces new techniques at each stage of the I/O pipeline to achieve high-performance I/O on these distributions. First, we introduce the Aggregation Tree I/O strategy to create the aggregation groups by constructing a tree that assigns a similar number of particles to each output file. Next, the binned attribute tree is a new data layout for multi-resolution reads and range queries that incurs little overhead to store and can be built quickly during I/O. And finally, a single tree metadata file is output to provide file-level selective read access to the entire dataset. Our aggregation tree strategy rebalances the I/O workload by constructing a KD tree that assigns a similar number of particles to each file. By ensuring that the data within these files is spatially coherent, we're able to output a layout well-suited to post-hoc visualization. And we evaluate our approach on Stampede2 and Summit, and demonstrate that it outperforms standard file per process and single shared file I/O, and compared to our prior work, it's up to 2 to 2.5 times faster on non-uniform distributions. This work also proposes a visualization-focused particle data layout that balances between rendering and attribute query visualization read access patterns. This layout is built on a spatial KD tree augmented with fixed-size bitmap indices, and we achieve multi-resolution reads without memory overhead through a subsampling-based level of detail. And finally, the layout is specifically designed to be built quickly in parallel during I/O so that it can be written out directly by the simulation to eliminate the data layout conversion bottleneck. So here, this figure kind of illustrates the way this works, that the simulation directly outputs this layout, and then immediately the data is ready for post-hoc visualization, say in a streaming-based browser client, as I show here, visualizing this combustion dataset. So I'll first discuss the aggregation tree strategy used to rebalance the particle distribution for I/O while taking spatial locality into account. The aggregation tree creates load-balanced, spatially coherent aggregation groups for two-phase I/O. The load-balanced structure of these groups allows it to improve I/O performance for non-uniform distributions, and the spatially coherent structure of the groups allows our approach to output data in a visualization-tailored layout. Performance portability is achieved through providing a tunable target file size, which controls the number and size of aggregation groups and the number and size of files output, and also directly affects the amount of network communication that takes place during I/O. The optimal size varies across HPC systems depending on the I/O system used by that hardware and the network topology, for example. And it's exposed as a tunable parameter for this reason. I'll discuss how our aggregation strategy works through an example. Here we have a simulation with 40 particles on 16 ranks. And again, note that the particle distribution is non-uniform in that the number of particles vary, and it's not possible to bound only the ranks with particles with a box. So the adjustable uniform grid assumptions are violated here. And the ranks are numbered from bottom left to top right. So the aggregation tree to compute the group assignment is constructed on rank 0. And this construction begins by having all ranks send their bounds and the number of particles that they have to rank 0. This gives it a picture of the domain as shown here, where we have the bounds of each rank and the number of particles there. And in this example, we'll choose 6 particles per file to achieve the best I/O performance on this hypothetical HPC system. The aggregation tree is built to partition the space into regions with roughly even numbers of particles. To do this, split planes are placed at rank boundaries to partition the subdomains into domains that have a roughly even number of particles. These splits are placed on the longest axis, with x chosen in case of a tie, or in 3D x, y, then z. And to choose the best split, we evaluate the number of particles that would fall into the left and right subtree of A. So if we place the split here, we would have 16 particles on the left, 24 on the right, and the cost factor measures how uneven this split is, where lower costs are more even. So here we have a cost of 0.1. Splitting in the middle would give us a cost of 0.25, while on the rightmost side would give us a cost of 0.45. And so we will place the split for A at the red line here, which has the lowest cost of 0.1. This process is repeated for B, now splitting along the y-axis, where we'll place the splitting plane here. The point I want to make here is that the right subtree of B is complete at this point, even though it exceeds the target file size of 6. This is because an individual rank's data is not split, and so it can exceed the target size if a rank has more data than the target. Down the left subtree, we place the splitting plane for C and return to compute the right subtree of A. As I mentioned before, the splitting planes are selected on the longest axis of the current bounds. However, ranks without particles are not included in the bounds computation. So instead of computing this 3x4 grid, we will actually consider just splitting this 3x3 grid when picking which axis we're going to split along. And so since x breaks ties, we'll split again along the x-axis here and place the split for node D at this point. The same process is repeated, again ignoring the rank with 0 particles. And we place the split plane here for E and again for F. And finally for G. The aggregation tree build is complete when all the subtrees are at or below the target size of 6 in this example, or they cannot be subdivided further, as is the case of the rank 0's data. The leaves of this aggregation tree form our load-balanced aggregation groups. So I label them by the ranks that fall into each one spatially. The next step is to assign an aggregator rank who is responsible for receiving the data for each leaf and outputting it to disk. The aggregator assignment is not tied to the spatial distribution, but is rather evenly assigned throughout the rank space to ensure that the I/O workload can be distributed evenly among all the compute resources that are available, rather than clustering around high-density regions or nodes again. Rank 0 computes this assignment and sends each aggregator the list of ranks that are in its leaf, and sends each rank the aggregator that it's assigned to. Next, each rank independently transfers its data to its assigned aggregator, and ranks without particles do not send data. So if we come back and compare the I/O load balance achieved by the aggregation tree against our previous work on the adjustable uniform grid, we can also configure the adjustable uniform grid to output 8 files, giving us a partitioning like I show here. And if I label them by the number of particles that fall into each group, we can plot a histogram of the number of files on the y-axis and the number of particles per file on the x-axis, so a histogram of the particles per file. And we can look at the target size of 6 here, and we can see that the adjustable uniform grid provides a much wider distribution. So the standard deviation of file sizes is much higher, meaning that the I/O workload is less balanced, while the aggregation tree is able to much more consistently meet the target file size, which will in turn translate to improved I/O load balance and improved I/O performance, as I will show in the results. After receiving the data, each aggregator constructs a binned attribute tree over the particles to directly output the visualization-tailored data layout. The binned attribute tree is a new low-overhead data layout that balances between rendering and attribute query filtering read access patterns by combining a spatial KD tree and fixed-size bitmap indices. Furthermore, representative subsets of the data are stored at the tree inner nodes for zero overhead level of detail. The binned attribute tree layout is designed for fast parallel construction during I/O, so that it can be built without impacting I/O performance. This build is split into, so each aggregator builds the BAT independently on its local particles, and within each aggregator, the build is split into 2 parallel stages that are run in parallel to each other. The first is a coarse bottom-up KD tree build, and the second is a top-down KD treelets that are constructed within the leaves of this coarse tree. So given the set of local particles, the aggregator computes the Morton codes for these particles and sorts them by their code. The unique subprefix of these codes, say 12-bit subprefixes, give a coarser Morton curve, which is used to build the coarse tree. So all particles with the same prefix will fall into the same leaf of this coarse tree. And these builds are also in parallel. Then at the same time, a coarse parallel bottom-up tree build is performed. This is as described by Karras, just run on the prefixes to produce a shallow tree. And within the leaves of this coarse tree, treelets are built top-down in parallel to provide better tree quality within the leaves of these trees. The individual BAT treelet builds are serial, however each one is independent per leaf, and multiple treelets are built in parallel to each other. The first step of each build finds a set of particles for that treelet based on their Morton code. Then before splitting an inner node, a fixed number of particles are sampled to provide level of detail at the current level. So for example, the node A takes the blue particles and sets them aside, and then splits the remaining ones at their median. The same is done for B, and again. Leaves are created when the number of particles in a subtree fall below a certain threshold. After making a leaf, the bitmap indices for the attributes of the leaves particles are computed and merged up to compute the bitmap indices of the leaf node, and then are propagated back up the tree, merging with the level of detail particles to compute the bitmap indices for the inner nodes. The same process is repeated for C down the right subtree to compute the entire treelet. Each aggregator then independently outputs its binned attribute tree to a file. The file layout is specifically optimized for optimizing build time and to provide fast access to the treelets. The coarse tree and treelets are stored separately to avoid a serial tree merge step, while the bitmaps are merged into a dictionary to reduce memory overhead. Replacing the inner node bitmap indices with smaller IDs into this dictionary. And finally, the treelets are stored at page boundaries to provide fast read access. Finally, a single tree metadata file is output to provide file-level selective read access to the entire dataset. So recall that the aggregation tree itself is actually just a spatial KD tree over the domain, where each leaf corresponds to an aggregator file. This tree is then populated with attribute metadata by collecting the value range and the bitmap indices of each aggregator's BAT root node. So the received bitmaps are remapped to the global range and assigned to the corresponding leaves, and are then propagated up the tree. Rank 0 outputs this top-level metadata to a file, where leaf nodes in the metadata file reference the corresponding aggregator subfile. Viz tasks are then able to open this metadata file to read the subfiles as if they were a single file, while at the same time performing spatial and attribute filtering at the file level using this top-level metadata, and finer grain filtering within each subfile using the binned attribute tree stored in each file. So now I'll discuss the evaluation of our approach. We evaluated our approach on both uniform and non-uniform particle distributions, and I'll first quickly go through the uniform benchmarks. These are run on write and read scaling benchmarks on Summit, which has a GPFS file system, and Stampede2, which has a Lustre file system. And we compare with IOR and parallel HDF5. In this benchmarks, we perform a sensitivity study on the target file size, where each rank writes approximately 4 megabytes of data. So these plots show the I/O bandwidth in gigabytes per second on a log scale as we scale up in terms of the number of ranks, where higher bandwidth is better. So file per process I/O does not scale due to the overhead of creating many small files. On the other hand, single shared file I/O does not scale well due to the global communication and synchronization required during I/O. The aggregation tree can outperform both of these approaches by and can do so portably across different HPC systems to achieve up to an order of magnitude, two times to an order of magnitude faster writes than traditional approaches. This is done by adjusting the target file size to balance between essentially file per process and single shared file I/O by adjusting the number of files and the amount of communication performed to provide portable and scalable I/O. Similar trends are observed for reads, where the two-phase read pipeline outperforms traditional file per process and single shared file reads. The next set of benchmarks I'll discuss compare the performance of the aggregation tree against our prior work on non-uniform real-world datasets. The first dataset, the coal boiler, is a simulation of the injection of coal particles into a boiler simulated using Uinta. This starts with 4.6 million particles and ends with 41.5 million particles. So the bottom left shows the coal boiler dataset with the time steps labeled. The second dataset that we test on is a dam break. This is a classic 3D free surface water column collapse simulated using the ECP EXA-MPM mini app. And this has 8 million particles on 6,000 ranks, so a fixed number of particles. And we compare write and read performance on Stampede2 using the Skylake Xeon nodes. So this plot compares the total I/O pipeline time of the two approaches, so the entire time from calling the write method to returning back to the simulation control on the coal boiler time series. So orange shows our aggregation tree, and blue shows the adjustable uniform grid. Here we're showing I/O time, so lower is better here. And what I want to point out is that the improved load balance provided by the aggregation tree allows it to achieve up on average 2 times faster writes compared to the adjustable uniform grid. In this plot, we show the same comparison, so I/O time against of the two methods, again aggregation tree in orange, adjustable uniform grid in blue, but this time on the dam break, which has a fixed particle count, where the particles just move through the domain, creating an I/O load imbalance. Again, the improved load balancing allows the aggregation tree to achieve up to 2.5 times faster writes on average. And what I want to point out furthermore is that because the dam break has a fixed number of particles, and thus the output data size is fixed, we would expect an ideal I/O system to achieve constant write times. So here I put this flat bar across the plot because this shows where we would expect an ideal I/O system, say maybe not at 20 milliseconds, but an ideal I/O system should achieve constant write times for writing a constant amount of data. And so while the adjustable uniform grid is strongly affected by the changing distribution of particles, our approach achieves nearly constant I/O times on this dataset. In terms of future work, it would be interesting to explore how finer-grained aggregation groups could be created to further improve I/O load balance, and how our approach can be extended to other mesh types. I'd like to thank you for your attention. The code for the library and modified mini-app and scripts and the paper are all available on my website, linked here. And you can get in touch through email or Twitter. Thanks for watching.